All right. So let's start because number of classes has been less. They're somewhat lagging behind compared to other years. By the way, your questions have been set, so you can expect a lot of numerical problems. Okay, keep practicing from the books, and after we go through this real cycle parts, means the modifications to the actual cycles, I will also send you a set of problems. So you can expect problems from the ideal cycles or the real cycles with deviations from the ideal cycles. Most of the part will be on numerical problems in the question paper. And graphs and plots also may be there. Notes should be sufficient for studying, plus some problem solving from the books. Okay, so in the previous class, we were studying about differences between ideal and real cycles, right? And we noted that there are a number of differences which make the ideal cycle, which make the actual cycle deviate from the ideal cycle. So just I will repeat once quickly so that we again come back to the same page. So these important points or important deviations were, one was that the kinetic energy of the fluid or of the gases is important, changes in kinetic energy that we had ignored, and now that we have to take into account. And how did we do that? We did that by considering stagnation properties instead of static properties at all points. Okay. Just a moment, please. Okay, so we took stagnation properties instead of static properties at all the points, and by taking the stagnation properties, we can, if we just take the stagnation properties, that is sufficient. We can do the same cycle analysis in the same way what we have done, but instead of say T1, T2, T3, T4, we will have to take T01, T02, T03, T04 like this, and then we can calculate the pressure ratio also using the same equations. So P02 by P01 is T02 by T01 to the power gamma minus 1 by gamma. So same equations are valid still. It's only that now we are taking stagnation properties or total properties. And how to calculate that stagnation or total properties, that also we have seen. T02 by T01 is equal to T1 plus V1 square by 2Cp, where V1 is the velocity at that point. So this equation, how it comes? It comes from the enthalpy equation, which comes from the first law of thermodynamics, energy balance. So H01 is equal to H1 plus V1 square by 2. So from this we get T01 is equal to T1 square by 2Cp. And once you get T01, you can always get P01 using the isentropic relation, because we are assuming that isentropically we are bringing the fluid to zero velocity to get the stagnation property. So P01 by P1 is equal to, where is it written? P01 by P1 is equal to T01 by T1 to the power gamma by gamma minus 1 for any point. If it is P02, so P02 by P2 is equal to T02 by T2 to the power gamma by gamma minus 1. Okay, so we are isentropically bringing the velocity to zero. Okay, and reversibly, adiabatically bringing the velocity to zero. In general, you can say that for any point, the stagnation and static properties are related by P0 by P is equal to T0 by T to the power gamma by gamma minus 1. So for point 1, we will write P01 by P1. For point 2, we will write P02 by P2. Similarly, T01 by T1, T02 by T2, something like that. And to get the pressure ratio, we need the temperature ratio, and that we can obtain from this relation. T01 is equal to T1 plus half V1 square by 2Cp, or in general, T0 is equal to T plus half V square by 2Cp. This is static temperature, broadly written stagnation. So this was the first point. Second point was that compression and expansion processes are actually irreversible. Till now, we had taken them to be reversible in the ideal cycles, but actually they are irreversible, and this is actually the most important difference between the ideal and real cycles, because the most of the change in the efficiency comes because of this. So this is one of the most important factor which governs the, or which decreases the efficiency of the real cycle. So ideal cycle, we have seen huge efficiency. Huge means relatively 60%, 62% like this. But in real cycles, the efficiency is of the order of 40%, even less. So that drastic change, most of it comes because compression and expansion processes are irreversible. And why this drastic change comes in the efficiency? Because compression process actually requires a large amount of work input. So even if there is any inefficiency in that, then the increase in work input increases by quite a big margin. Okay. Unlike pumps. So if I have a pump where the work input is very less, even if it is inefficient, even if I require say 20% more work, the total amount of work required still will be very less. But for a compressor, if I need 20% more work, if it is inefficient, then that 20% extra work is actually a huge amount of work of the entire cycle. So lot of the turbine work will go into just running the compressor. As a result, the isentropic efficiency of the compressor and turbine is very important. Then we will see the other points today, that fluid friction results in pressure losses. So already fluid friction induced losses for compressor and turbine we are taking into account in point 2. But there are other places where fluid friction occurs, like the regenerator, both sides of the regenerator, then the combustion chamber. So all these pressure losses results in less turbine work output, because the pressure ratio of the turbine decreases as compared to the pressure ratio of the compressor. Just a second, my ear is hurting for some reason. Let us continue. Then we have seen point 4, complete heat exchange is not possible. This we have anyway discussed in the previous class. I am just repeating because these are important points. The complete heat exchange is not possible in a heat exchanger. Heat exchanger means the regenerator. Okay, in some books, it's written as heat exchanger. So we have to take or define a parameter called heat exchanger effectiveness or regenerator effectiveness. Then another point is that the chemical composition of the gases vary. Initially it is air, but after the combustion chamber it becomes a mixture of oxygen, nitrogen, carbon dioxide and water vapor. So the Cp and gamma varies, and also the temperature also keeps on increasing from the compressor to the combustion chamber, and in the turbine again it keeps on decreasing. So they are also the effect of temperature. So Cp and Cp of gas generally increases with temperature. So that also induces changes from the ideal cycle, where we have taken air as the working fluid for the entire cycle with constant Cp and gamma values. Then there are other minor losses. One is bearing and windage losses. Bearing losses means you have mounted the rotors, the rotating shaft along with the rotating blades. These are mounted on the casing, right? So this has to rotate, and this will rotate on bearings. So there will be some slight frictional losses, although they are well lubricated. And then there is something called windage friction losses, which is the moving parts actually cuts through the air at the edge of the between the moving part and the fixed casing. So that leads to some amount of losses. Okay. Then there is an increase in mass flow rate, in the cycle. So initially we have some certain mass flow rate of air that is used as the base mass flow rate. Okay, but because of fuel addition, that increases by around 2%. So that also needs to be taken into account for accurate calculation. And the final point is that the combustion is not 100% efficient. So although it's very efficient as compared to other types of engines, like say IC engines, which are not which are much less efficient. The combustion in IC engine is much less efficient. Here it is very efficient. We have discussed why it is very efficient, because large amount of air is present. Air fuel ratio is very large, and as a result, most of the fuel finds some air for combustion, finds some oxygen for combustion. Only a very small fraction of fuel may remain in in uncombusted form. Okay, so it's around 98-99% this conversion efficiency. This is the efficiency of conversion of the chemical energy that is present in the fuel, the calorific value of the fuel, to the heat output in the combustion chamber. Okay. So these are the points that we want to study, and among this, the point 2 is the most important, which we will study in most depth. Okay. So first point, we have already discussed how to take into effect the kinetic energy change, and we had discussed partially the second point, the effect of irreversibility. What we had discussed in the second point was that instead of isentropic processes for the compressor and the turbine, so instead of going from 0,1 to 0,2s, so all the isentropic processes from now onward we will denote by the subscript S. Okay, so or just the extra letter S, so 0,2s instead of 0,2, and the actual state we will write as without the S. Okay, so instead of going from 0,1 to 0,2s, we are going actually from 0,1 to 0,2. What is happening is that the pressure ratio is kept constant, okay, by design. So we want to go from pressure of P01, which is the inlet pressure, to the pressure of P02. Okay, so this P02 by P01 is the compressor pressure ratio R, which is fixed by design. But instead of finishing at this point 0,2s, just a second, please. Some important call is coming. Hello, can you hear me? Hello.
Yes, sir.
We will continue. Sorry for the interruption. So yes, so instead of going from 0,1 to 0,2s, what is happening? Entropy is increasing, and we are going from 0,1 to 0,2. And as a result, what we can see, that 0,2 point is higher than 0,2s, because the constant pressure lines are moving upward. So we need more work, because work equal to Cp into 0,2 T02 minus T01, Cp into delta T. So delta T has increased, so more work is required. Similarly, what is happening for the turbine? This also we have read. So I'm just again explaining, just because we will continue from this part. So instead of going from 0,3 to 0,4s, we are going from 0,3 to 0,4. In the case of turbine, then on the contrary to the compressor, the work output actually is getting reduced. Okay, so because delta T is decreasing, so we are even if the same pressure ratio is maintained. So we are getting hit from both sides. Our compressor work is increasing, and our turbine work is also decreasing. Okay, so there is a double hit. So to the efficiency, so the efficiency is quite reduced in the real cycle. Okay. And if you are confused about what is the relation between the static points and stagnation points, how these changes occur. So for that reason, I have given a graph here to show you what are the changes. So the 1 point actually goes to the point 2. So the static process is the process like without measuring the velocity, like the static temperatures and static pressures. So the static temperature will be T1 at the inlet, okay, and the velocity is say V1. So the stagnation temperature T01 is T1 plus V1 square by 2 Cp. So this length this length is T is V1 square by 2 Cp is equal to V1 square by 2 Cp. Now the static process goes from 1 to 2, okay, instead of going from 1 to 2s. So it goes from 1 to 2. It follows this path instead of going from 1 to 2s, instead of following this, okay. So and at 2 again there is certain velocity v2. So T2 plus V2 square by 2 Cp is T02. So because we will be dealing with stagnation properties only from this point onward, we have here we have denoted the stagnation properties, but the static properties also, the efficiency, similarly efficiency can be calculated, but we will be using efficiency in terms of stagnation properties, okay. For static property, the efficiency will be T2s minus T1 by T2 minus T1 instead of T02s minus T01 by T02 minus T01. So this is what we had defined as efficiency for the compressor, the ideal work input by the actual work input. Similarly, for the turbine, we had defined the, for the turbine is opposite, right? Actual work is less. So actual work output by the ideal work output. So T03 minus T04 by T03 minus T04s. Obviously, for both cases, efficiency is less than 1. The way, that's why it is defined in this way. So then we did some calculations. These are not so important. This part only is important, the efficiency, because when you are solving the problem, we will be anyway calculating numerically. We will not be using this as formula. Never use this as formula. Okay, never try to memorize this. This is if you analytically solve a problem, then this comes into, means you are doing like this. But numerically, you will be calculating the value of P02 by P01, then T02 is all these things you can calculate. Okay. For example, if you want to calculate, just previous class I did not discuss. If you want to calculate the temperature at the compressor outlet, we'll see this in a problem in the next day, Friday, tomorrow's class. T02, if we want to calculate for a real compressor, non-isentropic compressor, and T01 and P01 is given, and pressure ratio is given. How will we do that? First, we will calculate T02s. So T02s by T01, what is? How will we calculate T02s? Can anyone say quickly? Very easy. Just I'm just uh, verifying that you understand. T02s by T01. So how will we calculate the T02s? T02s is equal to T01 into.
Isentrop
Sorry, voice got cut off. T02s by T01 is equal to P02 by P01 to the power gamma minus 1 by gamma, right? Because it's an isentropic process.
sir.
So P02 by P01 is the pressure ratio. Now pressure ratio will be defined in terms of stagnation properties. Okay, this is the pressure ratio, which is a given parameter. So that's why we can calculate T02s by T01. So because T01 is already known, T02s can be calculated, and once we know T02s, we can calculate T02 using the relation of efficiency, because T02 and T02s and T01 are already known. We can calculate T02. Like this, we can calculate for the turbine also. So we have done some calculations. I will just briefly remind you. T02s by T01 is equal to RC, which is the compressor pressure ratio to the power. Now the pressure ratios may be different also. In this case, it's same, but if there are pressure losses, it can be different also. That's why I had taken separate pressure ratio. So for compressor, it's RC to the power gamma minus 1 by gamma. And From there, after some calculations, we had found the work input to the compressor in terms of known parameters, which is equal to CpT01 Rc to the power gamma minus 1 by gamma minus 1 by eta c. Everything is known here. Okay. Similarly, for the turbine also, we found an expression. And we had also considered if the kinetic energy of the exhaust gas is lost, we cannot consider the total temperature because the extra enthalpy that was present because of the that could be recovered if the velocity could be recovered. Kinetic energy in the velocity could be recovered is lost actually in that case. So we have to take the static enthalpy in that case. So sometimes it is the efficiency of the turbine is defined like that. It depends on the situation. Okay. So typically it is defined like this only. Anyway, so again similar way WT can be calculated similar to previous case. And in case the pressure ratio is same for both, and there comes a situation, it can happen that the whatever work is generated by the turbine is entirely used up for the compressor. Okay, because the turbine work output is decreasing and the compressor work output is increasing. There may come a situation where the turbine work output is so less because of friction that it is equal to the compressor work input. This will happen when the compressor work input is equal to turbine work output, and if we equate this, we found a relation of temperature ratio T03 by T01, which is the maximum to the minimum temperature, is given in terms of R to the power gamma minus 1 by gamma by eta c eta t. At this point, we stopped in the previous class. Okay, so this temperature ratio, if it is this is the cutoff temperature ratio. Below this temperature ratio, you do not get any work output. Okay, so you want a temperature ratio which is higher than this temperature ratio. Okay. Now, this critical temperature ratio or cutoff temperature ratio depends on R. So, if R is larger, you want a higher temperature ratio because if R is larger, what happens is that the compressor work output is more, work input is more. So, the losses are also more. So, as a result, this cutoff point increases. Okay. And obviously, this cutoff point decreases if your efficiencies increase. So, if the compressor is more efficient or the turbine is more efficient, at low temperature ratio also you get work output. Okay, so this is how it is related. We will define another factor called work ratio, which is the net work output by the turbine work output. Turbine work output is the total work output from the turbine. And net work output is the turbine work output minus compressor work input. So this can be defined as WT minus WC by WT, or 1 minus WC by WT, or 1 minus what was WC, CpT01 by eta c. We will take the same pressure ratio R to the power gamma minus 1 by gamma minus 1 divided by WT, which is eta t Cp T03 R to the power. So just rearranging. So if you take out 1 by R to the power gamma minus 1 by gamma outside, inside you will get R to the power gamma minus 1 by gamma minus 1. Okay, so this gets cancelled and the Cp gets cancelled, and we are left with W net by WT, which is the work ratio, is 1 minus C. Okay, what is C? Previously we had defined C is R to the power gamma minus 1 by gamma. This we have taken to the top. So 1 minus R to the power gamma minus 1 by gamma divided by T03 by T01, which is T, eta C, eta T. Okay. So work ratio will increase if T is increased. If T increases, work ratio will increase. Means you get more fraction of work output as the net work output. More fraction as the net work output. Obviously, this will be true because if T increases, you are supplying more energy to the cycle. Okay, because T03 is higher, you are supplying more energy to the cycle, keeping the compressor work input same. So as a result, the overall net work output actually increases, efficiency increases. If eta c decreases, if eta c increases or eta t increases, if the efficiency is increased, then also this net ratio will increase because losses will be lower, you get net work output, more net work output. However, if R increases, then C will increase and the net work output will decrease, because with increasing R, your compressor work input increases, and as a result, the effect of irreversibility also increases. Okay. So now, what we are going to do, so this was related to the last class's discussion. Any questions? This part you might have been familiar previously, but now we will define a new type of efficiency, which you might not have studied, which is known as polytropic efficiency. Okay. So what we had defined, this efficiency, this is known as isentropic efficiency. Okay. Isentropic efficiency. So isentropic efficiency, we know how to define. Previously in thermodynamics class also you must have studied. So what is seen in real life is that this isentropic efficiency for a compressor or a turbine is not actually a constant value. Okay. What is seen is that if we increase the pressure ratio or change the pressure ratio, this isentropic efficiency changes. Okay. This isentropic, so for compressor, it is seen that the isentropic efficiency actually decreases with increasing pressure ratio. For turbines, it is seen that the isentropic efficiency increases with increasing pressure ratio. Okay. So it's not a fixed value. So taking it as a fixed value for very accurate calculations will lead to reduction of accuracy. Okay. So we need to find a parameter which is fixed, which gives the which incorporates the effect of losses. However, this parameter is fixed, whatever is the pressure ratio. Okay, if the pressure ratio is 5 or 10 or 15, it does not matter. This parameter should have a fixed value, unlike isentropic efficiency. So for that, we define an efficiency called polytropic efficiency. Now you might be confused why this name polytropic. So it will become apparent later on why this is called as polytropic efficiency. I want to take a 5 minutes break here. Okay. But suddenly I'm not feeling well. So I will take the break now itself, and then we'll continue for 1.5 hours after this. Am I audible?
Yes, sir.
We'll try to continue. I'm suddenly feeling lightheaded and dizzy. So I'm not sure whether we will be able to finish the class. Let us see. Maybe it will become better. Otherwise, I may need to go to the medical center. So we were discussing about another type of efficiency. You can see the screen also, right?
Yes, sir.
Okay. So which we call as polytropic efficiency. So this nomenclature will become clear later on why it is called as polytropic efficiency. But let us go on with this. So let us assume that this is a certain reason. So polytropic efficiency, it is defined in such a way so that it remains constant irrespective of the pressure ratio. Okay, so if the pressure ratio is increased from 5 to 15 or 20, it does not matter. The polytropic efficiency remains constant. So we will define it in a bit, but let us first try to understand why this is necessary. Okay, so the overall isentropic efficiency changes with the pressure ratio. It will become clear in a moment why it means how it changes. For a single stage, it is fine to use the isentropic efficiency. Okay, so for a single stage, which is just a small part of the overall turbine or overall compressor, we can use isentropic efficiency. May be suitable. Eta stage. Okay, we will call this isentropic efficiency as eta stage. It is the stage efficiency. So typically a compressor will have more than 10 stages. Okay. However, for the overall cycle calculation, fixed value of compressor isentropic compressor efficiency or turbine efficiency is not suitable. Basically, this is just summarizing our discussion. Okay. So let us try to look at it. What is happening? We'll keep this diagram open. Or we also need the text. So let us consider a three-stage compressor just for illustration purpose. So if it was fully the ideal situation, we would have gone from state 1 to 2s. So whatever we are discussing in terms of static temperatures, the same holds true for stagnation temperatures also. So instead of 0, 1, instead of 1 and 2, we could have written 0, 1 and 0, 2. Okay. So here I wrote as 1, 2 like this. But if you write as 0, 1, 0, 2, that also is exactly means totally correct. So from 1 to 2s would have been the actual ideal process. Okay. Now what is happening is that for the first stage we are going from, let us use this. Okay, and we'll keep this as reference because I can draw here and draw there also. So instead of going from here to here, we are going from here to here. Okay, this is the pressure. So this is the inlet pressure. This is the outlet pressure of the first stage. These are constant pressure lines. The red lines are constant pressure lines. So this efficiency, say this is a fixed efficiency, stage efficiency, isentropic efficiency of this stage. How will you define it? With this value, this delta T by this delta T, right? We already know that. So similarly, so this delta T we will call as delta T stage. Okay. For the second stage I have shown here. So second stage efficiency again in a similar way. Why this goes in this type? Delta T stage by delta TS stage by delta T stage. Okay. Delta TS stage by delta T stage. This is the isentropic efficiency of the second stage. Okay. So we will assume that for each stage the isentropic efficiency is constant because these are these are small pressure ratios, almost fixed pressure ratios. So the isentropic efficiencies are constant. At this point, we will assume like this. Okay. In future, we will not assume that. So this isentropic efficiency of the stage, eta stage, can be defined as eta stage equal to delta TS stage by delta T stage. Okay. Or delta T stage can be written as delta TS stage, means this value, by the isentropic efficiency. So this distance is not actual this distance, but this vertical distance, delta T stage, is equal to delta Ts stage by eta stage, where eta stage is the isentropic efficiency. Okay. Similarly for the third stage also. So if I sum up all the delta T stage values, so from here to here, then from here to here, and from the here to here. Okay. So we get T2 minus T1. So the overall change in temperature, actual change in temperature. So that is summation of delta T stage. So the summation of delta T stage is equal to, for each stage we have seen that delta T stage is equal to delta Ts stage by eta stage. So summation of delta Ts stage by eta stage. Eta stage is constant, so you can write summation of delta Ts stage. And in the denominator eta stage, okay, common eta stage. So this value plus this value plus this value by eta stage. Okay, this is the overall T2 minus T1. Okay. So we can write that now the overall efficiency of the compressor. What is overall efficiency of the compressor? Overall efficiency is T2s minus T1 by T2 minus T1. Okay. Let us call this T2s minus T1 as delta Ts. Okay. Using a different symbol. So this overall efficiency, eta C, let us call this as eta C for the overall compressor, not for the stage, is delta Ts, which is T2s minus T1 divided by T2 minus T1. Now what is T2 minus T1? It is delta T stage, right? T2 minus T1 is delta T stage, means this line plus this line plus this line. Okay. So now we can write using this expression 1 in this equation, we can write that eta C is equal to delta Ts by summation of delta Ts stage by eta stage. Okay. So eta C is equal to delta Ts by summation of delta C. So from this we can, what we will obtain is summation of delta Ts stage. Okay, we are removing this. Okay, basically we are removing this using equation 1. So summation of delta Ts stage by eta stage is equal to delta Ts by eta C. Okay. So now we will use this and we will keep this diagram open. Summation of delta Ts stage by eta stage is equal to delta Ts by eta C, just by using that formula. So what we are obtaining here is that, or if you rearrange the terms, what we are obtaining here is that eta C is equal to eta stage by delta into delta Ts by delta Ts stage, summation of delta Ts stage. So what is eta C? Eta stage, which we are assuming that it is constant for each stage, into the length of this line, is this value of temperature difference T2s minus T1 by summation of this minus this plus this minus this plus this minus this. So what about this term? Is it equal to 1 or greater than 1 or less than 1? The term within the bracket?
Less than 1.
Less than 1. Why? Because the constant pressure lines are diverging. So this length is greater than this length. This length is greater than this length. So basically sum of these lengths are greater than sum of these lengths, right? Because the constant pressure lines are diverging towards the right hand side. So that's why this is less than 1. So the overall compressor pressure, overall efficiency of the compressor is less than the stage efficiency. Okay. If you keep on increasing the number of stages, what will happen is that you will have lines like here, and these lines will be much farther away, even larger. So the effect will become more and more, means eta C will become even lower. Why? Because we are going farther away. Now comparatively this line is much smaller than this line. For this first stage, this was equal. For the second stage, this is slightly smaller than this. For the third stage, this is even smaller than this. For the fourth stage, this is much smaller than this. Okay, so the effect increases with increasing pressure ratio. Why does it increase with increasing pressure ratio? Because you are going further and further away towards the right hand side where the constant pressure lines are diverging. So eta C is less than eta stage, and it will keep on decreasing with increasing pressure ratio. Okay. Why? So to summarize this, so now you understand that we cannot use a constant compressor uh, efficiency, because if you use it, if you use it for a certain pressure ratio, then for another pressure ratio you need to use a different value. Okay, so it's a cumbersome process. Although for our course we will be using isentropic efficiency, because for course problems it is simple to solve using isentropic efficiency. But in real life you cannot do like that. Okay? When you are, if you are a designer working in some aerospace company, then you cannot do like that.
Sir,
Yes.
so you mean to say that at every stage the pressure ratio is going to decrease as we go ahead?
No, pressure ratio is fixed. So this, say if this is P1, this is say some value you can take P1 dash or P1A, P2A, sorry, P1B, something like that. So P1A by P1 is fixed. P1B by P1A is same. So all the pressure ratios are same. But the individual compressor efficiencies are also same. The individual, so sorry, this is wrong. Okay. Just a second. Select this. So the individual compressor efficiency, which is this line by this line, this is also same as this line by this line. So pressure ratios are fixed. But what is happening is that the deviation, if the line was totally idle, means if we had gone from this process to this process, that would have resulted in much less work input as compared to the actual work input for the fixed same pressure ratio. Okay, it's these lines are constant pressure lines, right? So here also whatever is the pressure ratio, here also the same pressure ratio exists. But because they are diverging towards the right hand side, we are seeing that the difference between this line and this line is very large. So the isentropic efficiency of this stage is this by this, okay, which is still the same as this by this. But this itself is now much larger than this. So the work input, actual work input increases much further as compared to if all the stages were ideal. If all the stages were ideal, we would have not had that problem. Okay. Is it clear, or shall I, like, what is it? I mean, what is the exact doubt that you have?
So just now you had said that there is a increase in work input.
Yes.
So that's also there was nothing else as at all.
Okay. There's an increase in work input. Yes. So to summarize, vertical distance between pair of constant pressure lines increase with increasing S. Okay. Okay. And as a result, what happens is that overall efficiency eta C is not equal to the stage efficiency eta stage. Eta stage is the isentropic efficiency of the stage, but it is actually less than eta stage. And this difference between eta C and eta stage increases with increasing the number of stages. All this we have already studied now. This is just a summary in case you read later. Why this happens? Because because there is an increase in temperature due to friction, which results in more work required in the next stage. Okay. Similarly, we will see that, or you can just do the same analysis. I mean, we will not show here that for the turbine, the opposite thing happens. For turbine, if you keep on increasing the pressure ratio, the efficiency of the turbine increases as compared to for the single stage. Why this happens? Because is there any diagram of turbine? Okay, if you consider this, so ideally we should have gone from here to here, but actually we are going from here to here, right? So instead of finishing at this point, we are finishing at a point which has a higher enthalpy. So the next stage will start from somewhere around here. Okay, there is a next stage. We'll start from somewhere around instead of starting from here. So this extra energy that is present because of losses in the previous stage is actually not lost because it can be used up for work output. This extra enthalpy can be used up for work output in the next stage. So frictional heating is this distance. Because of losses in the previous stage, some of it can be partially recovered in the next stage. Okay, so the overall efficiency increases with increasing pressure ratio for the turbine. So that now that dictates that because this is not constant, this overall efficiency, we need another approach. Okay, so there is another approach for calculating the overall efficiency of a compressor or turbine. Okay, to calculate the overall efficiency, eta C or eta T, we will define a parameter which is known as polytropic efficiency. Overall efficiency is not equal to polytropic efficiency. We'll define a parameter called polytropic efficiency, which will give us a relation to the overall efficiency. Okay. So what is this polytropic efficiency? This is also called a small stage efficiency. So if you divide a process into an infinitesimal process, okay, if you consider this graph here, if you divide the process into an infinitesimal process, okay, means infinitesimal pressure difference. In that case, the efficiency can be written as dTs, okay, which is the length of this line, by dt, which is the length of this line along the deviated line. Okay, so the vertical line by the deviated line. It's difficult to draw here with the mouse. If it was board, it would have been easier, but you can understand from my diagram. dTs by dt. So this efficiency remains constant whether you draw the line here or if you take another region. So if I take a pressure difference here, a small pressure difference here, there also the efficiency will remain same. If you take another place, this will remain same. Why? Because this depends on the, so this is for a very small pressure ratio. Okay, so here it just depends on the frictional losses. Okay, so wherever you take this, this is like the single stage efficiency, but even more accurate, means it is like an infinitesimal stage. So this dTs by dt, always it is seen that it always remains constant. Okay, and it is even constant if you compare different compressors. Okay, so it depends on the manufacturing process. So the manufacturing tolerances, what is the surface finish of the blades and things like that. So so if you have a plant, say Rolls-Royce production plant or a GE production plant, so from a line they are creating the turbine blades and then find the final engine. So the polytropic efficiency of the compressors and the turbine blades, or the turbine stages or the turbines that are created will remain constant if the process is same process and same devices are used. Okay, it will depend on the tolerances, surface finish, things like that. So this remains constant. Okay, so this efficiency is known as polytropic efficiency and it is written as eta infinity comma c. Okay, infinity, why? This is infinitesimal. Okay, so eta infinity comma c for the compressor, it will be eta infinity comma t for the turbine. So eta infinity comma c, so polytropic efficiency is equal to dTs by dt, and it is constant wherever you take it. It is constant for the entire process. Okay, so now let us formally define polytropic efficiency or small stage efficiency. It is defined as a isentropic efficiency of an elemental stage. Okay, it is still the isentropic efficiency. The way we have defined it is still the isentropic efficiency, dTs by dt. But for an elemental stage, for an infinitesimal stage, it is defined as the isentropic efficiency for an elemental stage in the process such that it remains constant throughout the process. Okay. So This is how it is defined. Any questions? We'll proceed further, but any doubts or anything which is not clear regarding this polytropic efficiency? This is by definition, it's like that, but it is seen from practice that this remains constant throughout the process, wherever you take it, even from different devices manufactured from this, like different compressors manufactured using the same devices or same tolerances, same surface finish, similar thing. Okay. So what has happened over the years is that during, if I compare the compressor from 1960s to say 2020s, this polytropic efficiency has kept on increasing because of better and better manufacturing processes. Okay. So anyway, eta c, eta infinity c, polytropic efficiency is dTs by dt. Okay, this is constant. So let us try to relate it. How to find this now? You can say, because I cannot measure a infinitesimal difference. Okay, in a real life turbine or a compressor. But I want to know what is the polytropic efficiency of my compressor. But I cannot measure the infinitesimal temperature difference. So how will I measure? Or how will I calculate the polytropic efficiency? Okay. So we have to relate it to some known parameters. And here the known parameters will be the outlet and inlet temperatures, pressures, things like that. Okay. Because those are the things we can measure. So let us consider the isentropic process. For isentropic process, everybody knows that T is proportional to P to the power gamma minus 1 by gamma, or T by P to the power gamma minus 1 by gamma is constant. Okay. So now I will not take any breaks unless I feel like, again, I feel don't feel well. We'll try to continue to the end. So T by P to the power gamma minus 1 by gamma is constant for the entire process. For the isentropic, for any isentropic process. For any isentropic process, T by P to the power gamma minus 1 by gamma is constant. Or so here the isentropic process is this TS process. So the isentropic process we will denote by temperature variation in the isentropic process will denote by TS. TS is equal to some constant. It does not matter. Some constant into P to the power gamma minus 1 by gamma. And log of TS is equal to log of this term. So which is log of C1 plus log of P to the power gamma minus 1 by gamma. So log of P to the power gamma minus 1 by gamma can be written as gamma minus 1 by gamma plus multiplied by log of P. Okay. If you take a derivative of both sides, you get dTs by T is equal to gamma minus 1 by gamma dP by P. This is constant term. This has got removed after the derivative. So we are left with dTs by T is equal to gamma minus 1 by gamma dP by P. Now dTs is equal to dt into polytropic efficiency. Okay. So dTs by T is equal to dt into polytropic efficiency by T. Okay. dt is the variation, small variation in this direction in the actual process. Okay. Which is also temperature. So because that is also temperature, we can write like this. So eta infinity dt. So eta infinity C dt by T is equal to gamma minus 1 by gamma dP by P. Okay. And because this is a temperature, we can again integrate. So going from point 1 to 2. Now this is not an isentropic process. Okay. Going from point 1 to 2, we will integrate. So integration of this, okay, integration of this term from 1 to 2 and this term from 1 to 2. Okay. So this will give us, this is constant, right? By definition, this is constant. So this can come out of the integration. So eta infinity C ln T2 by T1, okay, is equal to gamma minus 1 by gamma ln P2 by P1, or eta infinity C. So polytropic efficiency is equal to log of P2 by P1 to the power gamma minus 1 by gamma. This is just taken inside. You could have written outside also. Divided by log of T2 by T1. Okay. Eta infinity C is equal to log of P2 by P1 to the power gamma minus 1 by gamma divided by log of T2 by T1. This is a very important relation from practical point of view. Why is this an important relation from practical point of view?
Because of pressure and temperature are known in this equation.
Good. So because in this equation, the inlet pressure can be measured, inlet temperature can be measured, outlet pressure can be measured, outlet temperature can be measured. And then based on those measurements, we can find out what is the polytropic efficiency of the compressor. Okay. So that's why this is a very important relation. So efficiency, polytropic efficiency of a compressor can be calculated from measured values of pressure and temperature at the inlet and outlet of the compressor. Okay. Let us see some more relations, how it is related to the isentropic efficiency. Okay, if I define an overall isentropic efficiency, T2s minus T1 by T2 minus T1, how is it related to the polytropic efficiency? Okay, or how is it related to overall isentropic efficiency? We will call as compressor efficiency. Okay, and we will also uh, see why it is called as polytropic efficiency. Why this nomenclature? Why the name called polytropic? So as you can see from here, eta infinity C dt by T is equal to gamma minus, it looks horrendous, this integration. Just remove this. Eta infinity C dt by T is equal to gamma minus 1 by gamma dp by P. After integrating, the same thing actually. After integrating, if you take the eta C here, okay, I can write gamma minus 1 by gamma by, sorry, gamma minus 1 by gamma eta C, eta infinity C. Okay, and then you can do the same integral, or you can just take from here. Okay, so you can take it to the other side, gamma minus 1 by gamma eta infinity C. So this entire term you can put inside. So what will you get? T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma eta infinity C. I hope this is clear. This is just algebra. So instead of, so this is nothing. This is just a value, right? So I can find a value n. I can find a value n such that n minus 1 by n is equal to gamma minus 1 by gamma eta infinity C. Okay, gamma is known. So for air, gamma is 1.4. Okay, for gases, ideal, sorry, for combustion products, it will be different, but it is known. So gamma is known, and eta infinity C is also known for that compressor, for any compressor. Okay, it can be, we have seen it can be measured, or from measurement it can be calculated. So this term is known. Okay, so we can find a value of n such that n minus 1 by n is equal to gamma minus 1 by gamma eta infinity C. So we can write this process as T2 by T1 is equal to P2 by P1 to the power n minus 1 by n. So for what type of process we can write that T2 by T1 is equal to P2 by P1 to the power n minus 1 by n for a polytropic process. What is a polytropic process? Any process where PV to the power n is equal to constant. Okay, where n can have any value. Okay, so all these processes, PV to the power gamma is also actually just a subset of a polytropic process. So we can think of it, of this process, we can think of this process as a polytropic process. Okay, instead of an isentropic process. This was the isentropic process, and this is actually like a polytropic process. Okay, which can be defined as T2 by T1 is equal to P2 by P1 to the power n minus 1 by n. So for this process, instead of PV to the power gamma equal to constant, we have PV to the power n equal to constant. Okay, so we can use n instead of gamma for all the calculations. So instead of gamma minus 1 by gamma eta C, if you use n minus 1 by n, we can think of it as a polytropic process with the exponent n, PV to the power n equal to constant. Okay, that's why this efficiency is called as polytropic efficiency, because as if the overall process is like a polytropic process. Now you can relate, you can find out what will be the relation between the polytropic efficiency and the polytropic exponent. This n is known as the polytropic exponent. Okay, so gamma minus 1 by gamma eta C is equal to n minus 1 by n, or sorry, gamma minus 1 by gamma, yes, eta C. So eta infinity C is equal to gamma minus 1 by gamma into n by n minus 1. Okay, this is obviously, this is by definition, this was equal to dTs by dt. Okay, so we get a relation between the isentropic exponent, polytropic exponent, and polytropic efficiency. Okay. So this process, actual process, can be assumed to be or best approximated as a polytropic process. These are still models, right? These are still mathematical models which we are trying to fit to the process. Process is a physical process. It does not understand maths. But we are trying all these equations, PV to the power gamma equal to constant, PV equal to nRT. All these are models which represents, or the physics which represents that process. The process is occurring, it does not have a mind, it does not understand. But these are models which gives us, or which shows the best, or which best captures what changes are happening in real life. So basically, in this case, it is seen that this process, actual process, is best approximated as a polytropic process with an exponent n, where n is defined as in this way. So n can be calculated in terms of eta c and eta infinity c and gamma. Okay, where eta infinity c is already known from inlet and outlet temperature and pressure. Is it clear?
Yes,
This
sir.
is the difficulty with online classes. Actually, I am animatedly moving my hand when I am teaching, but you are not able to see that. In my class, you would have seen that how I teach, means a lot of body language and hand motion, hand gestures. So anyway, I'm actually like with the flow. I'm drawing lines on the air also. Anyway, so the relation between overall compressor efficiency eta c and the polytropic efficiency eta infinity c can be obtained. Okay, so overall efficiency is for the overall process. Overall efficiency is T2s minus T1 by T2 minus T1. Okay, this is very familiar to us by this point, which can be written as T2s by T1 minus 1 by T2 by T1 minus 1, dividing both the denominator and numerator by T1. T2s by T1 is nothing but RC, which is the compressor pressure ratio, to the power gamma minus 1 by gamma minus 1. And what is T2 by T1? By definition, where we have defined it, T2 by T1 is P2 by P1 to the power gamma minus 1 by gamma eta infinity c. Okay, so RC to the power gamma minus 1 by gamma eta infinity c minus 1. Okay, so this is the relation between the overall efficiency, overall isentropic efficiency of the compressor and the polytropic efficiency. If you assume a fixed polytropic efficiency, as is the case, we can plot this with increasing value of R. I will show you the plot later. And you will see that the overall efficiency keeps on decreasing with increasing value of R. You can also write this as eta c is equal to RC to the power. So if you want to relate this to the polytropic exponent, you can write this as, this is RC to the power gamma minus 1 by gamma minus n minus 1 by RC to the power n minus 1 by n minus 1. Okay. Anyway, so the temperature rise T2 minus T1 can now be calculated instead of using isentropic efficiency. If I want to use isentropic efficiency for the overall compressor, we can use T2 minus T1 is equal to T2s minus T1 by eta c. Instead of that, if you want to use polytropic efficiency or polytropic exponent, we can do like this. T2 minus T1 is equal to T1 common, you take T2 by T1 minus 1, or T2 by T1, remember, is a polytropic process. So P2 by P1 to the power n minus 1 by n minus 1. So using the polytropic exponent, I can calculate what is T2 minus T1. Okay, if you want to write in terms of polytropic efficiency, n minus 1 by n, remember, is gamma minus 1 by gamma eta infinity c. So I can replace that. So this is equal to T1 P2 by P1 gamma minus 1 by gamma eta infinity c minus 1. Okay. So the entire discussion that we have had today is also valid for stagnation properties T01, T02. So if I replace all the T1, T2s by T01, T02, P01, P02, the entire, all these equations and derivations are correct. Okay. So this is what is known as polytropic efficiency. So let us summarize once again, because this is a new thing. So we have defined a efficiency, isentropic efficiency of an infinitesimal state, And we have defined it such that we know that this does not vary wherever you take. So this does not vary with any pressure ratio, anything. It is the efficiency of an infinitesimal state. And this we have called as polytropic efficiency. Then we have seen that how it can be calculated based on actual inlet and outlet parameters. Then we have seen how it is related to how the actual process is a polytropic process instead of an isentropic process. And we can relate the polytropic exponent, we can calculate the polytropic exponent n from the isotropic exponent gamma and polytropic efficiency. Or you can say that how the polytropic efficiency is related to the polytropic exponent. And then we have seen how to find the relation between the overall efficiency of the compressor and the polytropic efficiency, and also the temperature rise in the compressor. Why this temperature rise? We have denoted because it is important, because this will give us the work out input. Cp T2 minus T1 is the work input to the compressor, which is equal to T1 P2 by P1 gamma minus 1 by gamma eta infinity C minus 1. Okay. So although I have said that I will not take a break, but my throat is hurting, I will need a coffee. So I will take a break, 5 minutes break here, and we will continue this discussion. Okay. We will continue. Am I audible? And screen is also visible, right?
Yes, sir.
Any questions? We read this material, and if you have any questions, you can ask in the next class. I will. I don't know whether I uploaded it or not. Let me just check. Eight. And upload 9 also. Okay. So yes, so we have defined polytropic efficiency for a compressor. Now we will define the same thing for the turbine. Okay, I could have left it as an exercise for you guys. But I thought better because this is a new concept, better to define it. But we will use the same logic, and you can use same logic to derive all the similar expressions what we have derived. The expression will look slightly different, but the logic is same. Okay. So for a turbine, the polytropic efficiency is defined as a isentropic efficiency of an infinite small state such that the efficiency remains constant over the process. Same like compressor. So in this case, it will be dt by dts. Okay. Unlike compressor where it was dts by dt, here it is dt by dts. Why? Because dt is smaller than dts. So that's why it is dt by dts. Okay. And any location you take, dt by dts will be constant. Now dts by t is equal to gamma minus 1 by gamma dp by p, that we have already found. So instead of using dts, now what we will do is we will write same trick that we have used. dts is equal to dt by polytropic efficiency of turbine eta infinity t. Okay. So 1 by eta infinity t dt by t is equal to gamma minus 1 by gamma dp by p, and if you integrate and rearrange, we'll find that eta infinity t is log of t3 by t4 going from 3 to 4. Okay, so this integration will be t3 by t4 log of t3 by t4 into is equal to eta infinity t gamma minus 1 by gamma p3 by log of p3 by p4. After rearrangement, you get eta infinity t is equal to log of t3 by t4 by log of p3 by p4 to the power gamma minus 1 by gamma. The form is slightly different, but the logic is same. Okay, so this is how you can obtain the polytropic efficiency of a turbine in terms of input and output, inlet and exhaust parameters. Okay, which can be measured. Inlet and exhaust parameters can be measured. The inlet temperature, exhaust temperature, inlet pressure, exhaust pressure, and we can find the polytropic efficiency of the turbine. So eta infinity t can be calculated from measured values of P and T at the inlet and outlet of the turbine. So similar to the previous case, now we will find a relation between polytropic efficiency and the exponent. So this is also like a polytropic process. Okay, we will see now that this is like a polytropic process going from 3 to 4. So eta infinity t is equal to log of t3 by t4 by log of p3 by p4 to the power gamma minus 1 by gamma. And so from here you get, by integrating, you will get t3 by t4 is equal to p3 by p4 into gamma minus 1 by gamma into eta infinity t. If you take this inside the log, okay, that will result. So instead of using gamma minus 1 by gamma eta infinity t, again we can write, if we can find a value of n such that n minus 1 by n is equal to gamma minus 1 by gamma eta infinity t. This n is the polytropic exponent for the turbine process, actual turbine process. Okay, so we can think of the actual process as a polytropic process with exponent n, where PV to the power n is constant. This n is different n as compared to the compressor. Okay, this has a different value. This is not the same n, and the expression is also different. Okay, if you take a look at the expression, you will see that it is different. I will show in a minute. So from here, it is clear that eta infinity gamma minus 1 by gamma eta infinity t is equal to n minus 1 by n, or eta infinity t is equal to n minus 1 by n into gamma by gamma minus 1. Okay. So this is the relation between polytropic efficiency of the turbine and the polytropic exponent. Okay. For the compressor, it was like this. It was just the opposite. Okay. Gamma minus 1 by gamma into n by n minus 1. Here you get the opposite form, because the turbine process goes in the opposite direction. That's why we are getting all this opposite behavior. Again, similar to what we have derived, we can derive for the turbine also the overall efficiency and the relation between the overall efficiency and the polytropic efficiency. Okay. Let us do that. Would have again left it as an exercise, but for the sake of completeness, we will do it in the class. Eta t is equal to T3 minus T4 by T3 minus T4s. Again, you do the rearrangement. So this is equal to 1 minus T4 by T3 by 1 minus T4s by T3. T4s by T3 is a isentropic process. You can write that as pressure ratio P3 by P4s. Sorry, P4s by P3 to the power gamma minus 1 by gamma. Now P4s by P3 is equal to 1 by P3 by P4s. So I can write this as T4s by T3 as 1 by RT to the power gamma minus 1 by gamma. Similarly, T4 by T3 we can write as 1 by T3 by T4, and by definition of polytropic process, T3 by T4 is P3 by P4 to the power n minus 1 by n. Okay, or it is equal to eta infinity gamma minus 1 by gamma. So I can write this as 1 by P3 by P4, which is RT, to the power eta infinity gamma minus 1 by gamma. Okay. So our relation between the overall efficiency, overall isentropic efficiency of the compressor and the polytropic efficiency of the, overall isentropic efficiency of the turbine and the polytropic efficiency of the turbine can be written in this form in terms of the variable RT, where RT is the pressure ratio across the turbine. Okay. So in this case, if I plot it, if you can easily plot it using MATLAB. I'm not plotting it using MATLAB, but you just take different values, take an array of RT and plot it for different values of RT. You will see that the efficiency of the turbine actually increases. It's increasing R instead of decreasing. Okay. And finally, we can find the temperature drop across the turbine. Why it is important? Because we want to calculate the work output of the turbine. Work output is Cp T3 minus T4. So we want to calculate T3 minus T4. It is almost analogous to what we had done and discussed in detail for the compressor. Okay. So T3 minus T4 is equal to T3 1 minus T4 by T3, which is equal to T3 1 minus 1 by RT to the power n minus 1 by n. Okay, where n is the polytropic exponent. This is equal to T3 1 minus 1 by RT eta infinity t gamma minus 1 by gamma. So you can relate, you can find out easily T3 minus T4 either in terms of polytropic exponent or polytropic efficiency. Anyway, if one of them is known, the other one can be calculated, and this can be calculated based on the inlet and outlet temperature. Again, like previous discussion is valid, fully valid for T03 and T04 instead of T3 and T4. I could have written entire thing in terms of T03 and T04 also. So this is how the variation looks like. Okay. So if you plot this eta t with respect to R, okay, with increasing value of R, you get increasing efficiency, overall efficiency. Okay. And at R equal to 1, the efficiency is equal to the polytropic efficiency. Okay. Because R equal to 1 is just like at the limiting point, like a very small infinitesimal pressure ratio. So the efficiency is also infinite for infinitesimal stage. So it is like a polytropic efficiency. Similarly, for the compressor also, just at the limit R equal to 1, it is like a very infinitesimal stage. So it is like the efficiency is like the polytropic efficiency. But with increasing R, the polytropic efficiency decreases for the compressor. Okay. Just the final point on this entire discussion. Do not get confused with all this terminology. Okay, ultimately eta C or eta infinity C or eta T or eta infinity T are the same information, but in different forms. Okay, they contain the same information. What is that information they contain? They contain the information about the losses that are happening. Okay, the frictional losses that are happening, viscous losses that are happening in the turbine or the compressor. But we are expressing them in different form, in the form of either isentropic efficiency or polytropic efficiency. But ultimately, the physical process does not bother about what terminology we are using. Physical process is occurring, just it will occur with some frictional losses. So we are putting different names to different terminologies. Ultimately, it is just to represent the same thing, losses that are happening. Any questions? So next, what we will do is we will go through the other factors. Okay, other factors are minor factors as compared to what we have discussed. So we can quickly go through them. We have gone through first point, second point. Okay. These are all the points we will go through. But we don't need to go through in this kind of detail for the other points because those are much more minor, easily accounted for. Minor means easily accounted for. Minor does not mean that the effect is less. Effect can be quite high also. Still, it should be less as compared to the losses in the compressor and turbine because those are the most major losses. Unfortunately, this scanning here got cut off. So, but you will be able to understand. So third is the effect of pressure losses. Okay. So how to take, where are the pressure losses occurring? One pressure loss occurs at the regenerator on the compressor side regenerator. Okay. Regenerator, remember, it's a heat exchanger. So you have two sides. One is the flow from the compressor, which is getting heated. One is the flow from the turbine, which is the temperature is going down. This diagram is wrong in one way. Can you say why it is wrong? Why it is wrong? Although it's just for showing the losses, but later I realized that there's a small mistake here. What is the mistake? It is a known mistake to you. Means even if you don't know about pressure losses, you will be able to find the mistake.
Entropy is getting reduced in 0406. So
That can get reduced because there is heat loss. If you extract heat from, so that is again a common misconception, right? That entropy always increases. For a single process, entropy can decrease. If I keep a cup of, right now I have a cup of hot coffee in front of me, its entropy is decreasing. Okay, but the surrounding entropy is increasing. So if I add the total entropy is increasing. But for a single process, which is the process of cooling of this coffee, the entropy is decreasing. Because here the gases are getting cooled, its entropy can decrease. Entropy can decrease. That is not the error. It's actually a very common question in the interviews that we ask. Anyway, this it's a minor mistake. This 0.2 point should have been lower than 0.6. Why? Or 0.6 should have been higher than 0.2. Because how will I, so this gas is used for heating this gas, right? How will I heat the gas from 0 to, if my gas itself is at a lower temperature, what will happen? Heat will flow in the opposite direction, right? So because this diagram looks complicated, you have got confused. If I had shown without the pressure losses, you know that this 0.5 should be at least lower than 0.4 or equal to 0.4, and this 0.2 should be at least equal to 0.6 or lower than 0.6. Otherwise, heat exchange cannot, heat exchange will occur in the opposite direction. Okay, so that's the actual mistake. It's a minor mistake, but still you have to be careful about small details also. Anyway, is it clear what I said?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So the pressure loss occurs in the heat exchanger in the regenerator from 0 to 0.5. So what we can show is very difficult to show here in the diagram, but drawing for me we also with a mouse will be very difficult. If it was a chalkboard, I could have shown. So instead of following the constant pressure line, blue line, we are going to a lower constant pressure line, this red line. Okay, we are going to this line. So there is a pressure loss from 0 to 0.5. Okay, we can call this pressure loss anything. So we'll call this delta P region A. Okay, the pressure loss in the regenerator on the A side means the one of the sides. Other side we will call as delta P region B. Okay, so on the other side of the regenerator, there is a pressure loss. We are, instead of following P04, we are going to this lower pressure line. Okay, P06. So this is delta P region B. So what is the role of this pressure loss on the turbine work output? Is P04 fixed or P06 fixed? Which one is a fixed value variable?
P06.
P06, because it is the atmospheric pressure, ambient pressure. You open, because ultimately after the regenerator, the exhaust gas goes out and it goes out at the ambient pressure. Okay. So P06 equal to ambient pressure. Now, if there was no pressure loss, P04 would have been equal to P06 and we would have obtained larger work output. But because of this pressure loss, we are getting less work output. Although I have drawn it in an exaggerated way, actual pressure loss may be 2%, 3%, 5%, but still, this is reducing the turbine work output. Similarly, this also will reduce the turbine work output because you are, instead of pressure P02, you are starting from a lower pressure. Okay, so we are going from P02 to P05. P05 is a lower pressure. Then there is a second loss in the combustion chamber. So again, like 3 to 4% pressure loss occurs in the combustion chamber, and you cannot avoid it. If I make the flow to be very streamlined in the combustion chamber, there will be very less pressure loss, but then the combustion cannot be sustained. So we need to create some turbulence in the combustion chamber to sustain the flame. Okay, that will be clear later on when in the second half of the course, towards the end of the course, that how the circulation is made in the combustion chamber. You need recirculation zones so that there are local regions of low velocity where the flame can be sustained. But creating this recirculation zone has an adverse effect on the pressure. So there is a pressure drop. Okay. So we are going from P02 to P05, slight decrease in pressure, and then from P05 to P03. P03 is the other blue line here. It's very difficult to distinguish, but hopefully we will be able to distinguish. There are three constant pressure lines. One is P02 line, one is intermediate P05 line, and one is even lower P03 line. So we are going from P05 to P03. Okay, so 05 is at a higher pressure than 03. 03 is the combustion outlet condition and 05 is the combustion inlet condition. Okay. If there is no regenerator, how will the cycle look like? We'll go from 01 to 02. From 02, there will be a loss to 03. And from 03, we'll directly go to 04, which will be at the outlet pressure. Only single pressure loss will be there in the combustion chamber. What are the law? So this combustion chamber pressure loss is denoted by delta PC. Okay. What is the role of combustion chamber pressure loss and delta P region A? It also decreases the turbine inlet pressure. As a result, the work output is reduced. Okay, so P03 by P04 is much lower than P02 by P01. Just a second, please.
So you were muted.
Hello, am I audible? Hello.
Yes.
Yes.
I think some internet issue was there. My screen was showing that I am there, but trying for a long time. Anyway, can you see the screen now?
Yes, sir.
Okay, okay. Anyway, so okay, so these pressure losses, the role is that means role is adverse role basically. Unfortunately, the turbine work output decreases. Okay, so just to summarize, pressure losses occur in the combustion chamber and both sides of the regenerator. Okay, pressure losses will also be there in the intercooler if there is an intercooler, and second combustion chamber if there is a reheating process. Pressure at each point can be calculated based on the losses, obviously, and fed into the cycle calculation. For example, if we want to calculate P03, we can calculate in terms of P02, which is the compressor pressure output, minus the pressure losses, delta P regen A. Obviously, this has to be measured or given to you as a problem. So in our course, this will be given to you, but in real life, you have to measure it or find it from some correlation. What is the pressure loss? P03 is equal to P02 minus delta P regenerator A minus delta PC. Okay. Sometimes it is better to use the pressure loss as a proportion of the inlet pressure. Generally, it is defined as percentage of pressure. Okay. Pressure loss. So for combustion chamber, it is written as P03 is equal to P02 if you take common 1 minus delta PC by P02 minus delta P regen A by P02. Okay. So for the inlet side, this is generally defined in terms of percentages, like 2%, 5%, like this, even for the regenerator. For the outlet side, it is defined as a, generally it is defined as a value instead of pressure ratio, instead of percentage. For the inlet, it is defined as a percentage because this compressor outlet pressure is the important pressure. This is the peak pressure in the cycle. So based on this, what is the loss that is defined? Typical values are 2 to 3% for the industrial turbines and 6 to 8% for aerospace applications. In the problems also, I give this like a 4% pressure loss is occurring, something like. Now, can you say why this pressure loss is less for industrial turbine and high for aerospace turbine? Using logic. No idea why this pressure loss is happening in the combustion chamber. Just now I had explained. We could have streamlined the combustion chamber so that there is minimal pressure loss, less than 1%.
Flame propagation speed is lower, so it is important to slow down the flow.
So it is important to slow down. So we need to use some recirculation, basically to hold the flame, sustain the flame. So sustaining the flame in a jet engine is much difficult as compared to industrial turbine, because your inlet velocity, you have a very large inlet velocity in the jet engine. So sustaining the flame is difficult. You need more mechanisms for holding the flame. As a result, the pressure losses are higher. Okay, it need not be 6 to 8%. Recently, it can be as low as 4% or similar to that. Okay. The role of pressure loss is that it's an adverse role. It reduces the network output. Okay. So similarly, we would go to the next point. That is the effect of regenerator loss. Okay. So that we have already discussed previously. Regenerator in terms of regenerator efficiency. Okay. We define regenerator. So what is the regeneration process? Energy balance. So in the turbine side, the mass flow rate of the turbine, like from the turbine, mass flow rate of the exhaust gases into Cp of gases. We are taking different Cp for like here for just for the sake of writing. In the calculation, we may use same Cp also. Into T04 minus T06. This is the energy that is lost from the regenerator from the exhaust gases side. And this energy is used for increasing the temperature of the air coming out from the compressor. So this should be equal to mass flow rate from the compressor into Cp of air on this side into T05 minus T02. So temperature rise in the compressor after the compressor. So if Cp is taken as constant and mass flow rate is taken as constant, T04 minus T06 is equal to T05 minus T02. Okay. So T04 and T02 are known values. T02 is the compressor outlet temperature and T04 is the turbine outlet temperature. And T05 and T06, typically T05, we if it is a 100% efficient regenerator, what should be the value of T05? 100% efficient effective regenerator. What should be the value of T05? You guys are not reading previous material. It is not needed to read also, just common sense. What is the maximum temperature that can be obtained theoretically?
T04.
It is equal to T04. So T05 should be equal to T04 ideally, and T06 should be equal to T02 ideally. We have studied, right? It's T02. If we can, means if T05 is equal to T04, T06 will be equal to T02. Okay. But in real life, what happens? We cannot have 100% effective heat transfer. So we define a regenerator effectiveness, which is given by T05 minus T02 by T04 minus T0. How far below T04 we are reaching? Okay, if the regenerator effectiveness is 100%, if this value is 1, and T05 will become equal to T04. We have discussed previously, if you remember, this value is typically around 0.9. Okay, it can be increased. How this can be increased? It was written below, so I have hidden it. How this value can be increased?
By like increasing the length of the heat exchanger.
By increasing the surface area, of the heat exchanger. But what is the drawback of that?
Pressure drop will be higher for
Pressure drop will be higher, so turbine work output will reduce. So there is a compromise there. So we cannot increase indefinitely. To increase the value of epsilon, larger surface area is required, but the pressure drop will be higher. Okay, so you cannot make a very large. And another thing is that the mass will be very large. So and the system cost will also increase. Anyway, we cannot use this for aerospace applications, regenerators, intercoolers, or like regenerators and intercoolers. Only for industrial gas turbines, these are valid. Still, if you don't want it to be very, very large. Okay. So this is how it needs to be taken into account. It's very easy. Means if in a problem point it is specified, or in the actual calculation it is specified that regenerator effectiveness is 0.9. So we can find what is T05 from this expression. Instead of using T05 is equal to T04, we have to calculate T05 from here. Okay. So the next point we will discuss in the next class because our time has run out. So some other points are there. And then we will see some plots using MATLAB of real cycles, how the all these efficiencies decrease for a real cycle. All these plots we will see using MATLAB, and you can also plot similar plots. I will give you some assignment because this very few classes were there before the midterm. Most of the course will be taught after the midterm, and then only I can. So after I teach the jet engine part, at least the turbojet and turbofan, then I will give you some assignment. Assignment means not this numerical problem. Numerical problems I will give to solve for practice before the exam, but I will give you some programming assignment so that you can also create similar plots what I am showing to you. But for turbojets, for turbojets also I will show. For turbofans you can create. I will give you something like that, or for turboprops you can create, and it's quite interesting. You can study and draw different plots. We'll stop here and we'll continue our discussion in the next class. Question is already set as I have discussed, and in the beginning of the class, question has been submitted by me, and you can expect a lot of numerical problems. Okay, it may be simple or not simple depending on your how is your understanding. So it is. I have not given very tough problems, but based on whatever we have discussed in the class, and you can go through similar problems in the book. I have just created a few problems. So that type of numerical problems you can practice. And maybe there will be some graphs and small questions, okay, as I usually give. So let us stop here. Attendance I will take from the portal.